morning, everybody, and welcome. I'm Savannah, your host here for Dirty Talk. Thanks for coming on the show today, Dr. Bell.
Thank you for having me. I'm Dr. Carly Bell from the Soil Sciences Department at UMass Amherst, where we study all things dirty.
All right, and today we're going to talk about how to measure organic carbon in soil, correct?
Indeed.
Okay. So can you tell me the overall importance of knowing the organic carbon concentration in soil?
Sure. It's important because depending on the ecosystem and concentration of organic carbon, it can affect the way the soil acts physically, chemically, and biologically.
So when we're looking at the soil after, say, the devastating wildfires in Australia, how might we suspect the fires to have changed soil?
Well, wildfires, depending on their severity, can either have a positive or negative impact on the soil ecosystem.
Oh, positive? Really? How?
Low-impact burning can actually promote the growth of flora, increase available nutrients for vegetation, and thin overcrowded forests.
That sounds fantastic. So, how can more severe fires affect the soil?
More severe fires can often change physical effects such as hydraulic functioning, accelerated erosion, leaching, or denitrification. Wildfire can affect soil by changing the rate of succession.
Excuse me, 1 second. What does succession mean?
Glad you asked. Succession is how the ecosystem changes over time, especially after a disturbance.
Okay, thank you. Continue.
Biologically, wildfire can also affect species composition, population, and diversity of fauna and microbial species. The soil can lose valuable nutrients to ash and smoke columns, carbon to nitrogen ratios can change, and mineralization rates can change, causing imbalance in the system.
Wowzers, that is bonkers. So, how can we measure all of that to compile trustworthy results about the impact of the wildfires in Australia?
First, we must determine the soil type being tested. We can conduct an initial textural analysis using the pipette method. This method uses a combination of chemicals to break up the soil aggregates and oxidize the organic compounds. Then we physically agitate it and use Stokes' law to relate the rate of particle settling to the particle size. This is a pretty inexpensive and relatively straightforward method to determine soil type.
After the soil type is determined, now what methods to use from there?
There are many methods to determine organic carbon in soil. We must first determine which method to use, since there is no standard method yet.
No standard method? Then how do you determine which method to use? How can you compare your results or replicate any experiments without a standard method? That's crazy!
Well, Savannah, there's two main methods of determination, wet and dry combustion. They each have pros and cons, so there's controversy within the community on which method should be the standard. It's an ongoing issue that must be resolved.
I see. What a dilemma. So, which method would you recommend?
Well, one of my fellow colleagues actually conducted some research in Brazil comparing the effectiveness of several methods. They concluded that the elemental analysis method should be the standard to compare other methods' results to, since it is considered the standard for total soil carbon.
Interesting. So, what's involved in conducting an experiment using the elemental analysis method?
Though it may sound complicated, this is one of the most straightforward processes. My colleague passed a soil sample through a fine mesh sieve, which was then combusted at 975 degrees Celsius in a capsule. An automatic analyzer detected the thermal conductivity of the sample.
An automatic analyzer. What are some of the benefits and drawbacks of using it?
While the equipment used makes the process easier, maintenance and calibration must be upkept. It can also be expensive to purchase and repair and can't be used easily outside of a laboratory setting.
What are some of the other methods that your colleague tested? How did they compare to elemental analysis?
The Möbius method actually proved to have the closest results to elemental analysis, with an R-squared value of 0.87. The sample is passed through a fine mesh sieve and placed into an Erlenmeyer flask. Potassium dichromate and sulfuric acid were then added and mixed well. It was heated to 100 degrees Celsius for 30 minutes. Phosphoric acid and diphenylamine were then added, and excess dichromate was titrated with ammonium ferrous sulfate, also known as Moore's salt.
Wow, that sounds like a pretty complicated procedure. Were there any other methods tested that compared well?
Actually, yes. My colleague also tested what's known as the colorimetric method. This passed a soil sample through a sieve and placed it into a Erlenmeyer flask. Sodium dichromate and sulfuric acid were then added, and the mixture was placed into a shaker. Afterwards, it was left to settle for an hour, then distilled water was added. The supernatant liquid was decanted and collected, and the absorption rate of the solution was measured using a photoelectric colorimeter, calibrated to account for different concentrations of glucose. This method proved to have an R-squared value of 0.85, similar to the Möbius method.
Now that R-squared value seems pretty substantial as well. Did testing these different methods tell us anything important about which methods are more effective than others?
That's a good question. In fact, we learned a lot from testing the colorimetric method. We now know that it's possible to combine wet methods with photometric determination, which can be much more straightforward than titration as used in the Möbius method.
That sounds like an important result to me. Were there any other methods that proved to be less effective compared to elemental analysis?
While almost all of the methods tested had a relatively high R-squared value, the gravimetric method had the lowest, at only 0.66.
Oh, jeepers, that's a huge difference. Is there any hypothesis that could justify why this value is so low?
Because soil has different components, such as organic matter, minerals, aggregates, etc., some of those lose more water at high temperatures than others. Because of that, there can be variations in mass loss. We try to account for this by determining the mass of organic compounds lost in the form of carbon dioxide, but this leaves plenty of room for over- or underestimation.
So from these results, it sounds like research is being done to develop a better method of determining organic carbon in soil. In your professional opinion, what does the future of analysis of organic carbon in soil look like? And what are some of the things that you think can be improved upon?
While all these methods produced effective results, they can always be made more accurate and precise. We should strive to make refined instrumentation as inexpensive and easy to maintain as possible. It would also be helpful to have a method that can be used on the field to provide immediate results so further samples can be taken if necessary. Another drawback to almost all wet digestion methods is that they use toxic reagents, which should be limited as much as possible. These methods also require further analysis of the results to account for mineralization and other components in the soil. So if a method could account for this simultaneously, we'd be in business.
And these methods your colleague tested were based off of soil samples taken in the Savannah, Brazil, right?
Yes, that is correct.
So if we were to use these same methods on soils in Australia, would they perform the same?
Soil varies extremely depending on the ecosystem and climate, but I'm sure that elemental analysis, Möbius, and colorimetric methods would suffice, as these are the best methods we have currently.
Alright, well, what about in comparison to soil damaged by wildfires? Many scientists are concerned about how this will impact ecosystems in the future. Engineers, especially civil and environmental engineers, are also concerned about how these results could change building protocols and regulations.
Like I said earlier, wildfire can most certainly affect the properties of soil. Because of this, scientists should test the damaged soil for microbial and chemical changes that can either benefit or harm the ecosystem's succession, depending on the severity of the fires. As for civil engineers, they should be concerned with the chemical and physical properties of soil, especially how the damaged soil will now erode, absorb water, how much weight it can hold, and how it will react with different building materials.
Wow, who knew soil analysis could be so important? Thank you so much for your information and your time, Dr. Bell. Hopefully, we can innovate a better method in the future.